Alrighty, here's section 2.5, and this is example 2.5.1, and I wanted to point it out because it has something kind of interesting here. So it says if A and B are n by n, okay, so we've got a couple of square matrices satisfying a squared equals b squared equals ab quantity squared equals the identity. It says then prove AB equals BA. Now the thing here is, notice that we have a couple of different matrices such that they are their own inverse. Now this shouldn't be totally surprising because we do have a couple real numbers that are their own inverse. Now, of course, one of them is 1, right? Because if I take 1 times 1, I get 1. And on the other hand, though, if I take -1 times -1, I get 1. And so -1 is its own multiplicative inverse. So the fact that matrices some matrices might be their own multiplicative inverse isn't that amazing, but actually there are quite a few matrices that are their own inverse. So, that's just something to kind of keep in mind that I think might be overlooked if you're just kind of looking at their proof and so forth. So the solution here, the proof of this, they say, well, okay, assume what they're saying, so they actually say assume a squared equals b squared equals ab quantity squared, and that all equals I. Okay, then now from that assumption, if this is true, then A and B are non-singular. And they point out that A inverse is equal to A and so forth, right? So then A inverse equals A and B inverse equals B. So by saying A inverse equals A, I'm saying that A is non-singular and its inverse is itself. Same thing with B. And then similarly, because we squared the AB and got I, so I should have put a comma here, I guess, and then AB inverse is equal to A times B. And on the other hand, though, AB inverse, we know if A and B are non-singular, well, then we have a theorem that says that's its inverse. Okay, so if that's the case, right, then AB is equal to B inverse A inverse. But now multiply, or not multiply, sorry, but B inverse is its own, is B, sorry, and A inverse is A. And so we get that AB is equal to B times A. And that's what they wanted you to prove. Right. So pretty much when you look at that proof, then I wrote down what we were assuming to be true. Then I wrote down things that follow immediately from those assumptions, A inverses A, B inverses B, and AB inverses AB. And so the only real sort of trick here was to realize that, well, AB inverse, we also have a theorem about that, and that's B inverse A inverse. And so putting those together gave us what we needed, and using the fact that these were, each matrix was its own inverse, we got it.